Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
That Wilson Donnelly and I have been doing on Ethernet topology discovery. Now, I guess some of you have got networks at home, computer networks at home, and even if you don't, you probably realize that many people do, and you think that maybe one day you might. And if so, this is relevant for you. A bit of an outline just. I'm going to talk a little bit about motivation and then take you through an example, the way we organize the system, a few of the techniques that we use. I'm not going to go into that in too much detail for this audience, and because we have a short time, I talked about some of those in more detail at a serious talk. Sorry, Austin talked about these in more detail at a serious talk earlier in the year, and finally a bit of a summary. So this is how we came to the problem in the first place. You'll know that there's been various work happening here for a couple of years on various ways of doing quality of service, trying to improve management of network resources, trying to do things like admit video streams in the system, work out how a video stream ought to adapt automatically to contention or to load in the system in the network. So this is where we came to it. All of the systems that go about trying to adapt to network behavior, how much bandwidth is actually available to you in the system, how is your network behaving today, they can all benefit from knowing a little bit more about the topology of the system that they're actually using. What total components of the network are there? How are they interconnected? Which machines are sharing which links? If I go to introduce a new video stream in this system here, is one of the components going to be a bottleneck? And if so, which one? And which are the other streams that are using that bottleneck? And how should I adapt either to that or cause those other streams to adapt to the fact that I have to add this new video stream into my home system? So this is where we came to it. In fact, there turned out to be a whole bunch of other reasons why knowing the topology of your network is useful. This is one of the ones that most interests the guys in the Windows land. It's dealing with network errors or trying to give more informative feedback to the user. It turns out that if you look at the product support statistics, that networking problems or problems associated with networking are both the hardest to resolve and the hardest to understand and the most costly both for Microsoft and for other companies that provide support. Networking is difficult. It's very difficult for the technician even to understand exactly what the user's configuration is, to understand it. So being able to kind of map the network and understand what the problem is, perhaps, might just make things a little better. In this case, for example, suppose that upstairs in the kids' bedroom, the kids kick the power cable out of the back of this networking hub over here. It would be much more useful if the user can see the kind of map of the network and observe that all of the equipment in that room, both the PC and the Xbox, have disappeared from the network. And then maybe they can understand, gee, what's likely happened is there's something wrong with the network, rather than perhaps what they do at the moment, which is assume that one or more boxes need rebooted. And they do lots of rebooting of computers and swearing at Microsoft, and the problem still doesn't go away. And eventually they discover that somebody's kicked the power plug out. So it would be much better if they could just see some kind of representation of their network. Perhaps more optimistic is some idea of long-term being able to actually look at the network's topology and make specific recommendations to the user. Look at this left-hand network and say, well, in this case, you've got too many devices attached to this hub object and only a couple of devices attached to the switch object. And switches provide better performance than hubs. So what you really ought to do is to rearrange your network as follows, and you'll observe an improvement in performance. Maybe if you want to go to extreme lengths, you can imagine, a pop-up link that says, click here and go to the Microsoft.com/hardware website. We'll make a product recommendation. This is the thing you want to buy. It'll make your network perform much better or make your network much more secure. Type your credit card number in, and that'll all be very good. There's a couple of other more subtle things that you can do with it. Here's one of them. Is to think about forward planning, forward scenario planning. At the moment, if you think about what we do in products like Windows, is we imagine lots of subsequent particular uses or scenarios in which people might use computers or computer systems, and then we try and improve their experience for doing that. We provide more software, provide better software, and make it easier for people, that kind of thing. But it's quite difficult to do that for a network. How do we improve the home user's network experience? How do we make it easier for a consumer with 2 or 3 or several computers in the home, or some small office or small business, to make their network experience better. It's quite difficult because it's quite difficult to understand what typical networks look like. So here's something that we could do. Maybe Brendan might find this interesting. If you had deployed this kind of a system, then you could gather the topology from all of these small office and home networks. And any time maybe they could opt in, or when any time they do some kind of fault report, if it's associated with networking, what you do is at the same time as you do your Dr. Watson or your online crash analysis and you upload a fault report, at the same time you upload to Microsoft a brief snapshot of just what the topology of the network looks like the user has at home. And that makes it much easier then to understand what typical home networks look like from the point of view of network planning. And we can do things like use it to drive new deployment or use it to drive obsolescence. When is it okay to discontinue support for particular legacy nasty protocols or interoperability? Well, if you know that most consumers don't have that anymore, then it's time to turn it off. So here's the question you might be asking, which is, why is this research? Right? Lots of people have done network topology discovery before of various sorts. So what's different here? Well, the difference is, every time people have done this in the past, they've addressed the enterprise environment. They've assumed large switches that have SNMP, they have software on board, and they can use the simple network management protocol to interrogate the switches and extract information from the switches in the network about the network, and then build up the topology from that. So basically what they've assumed is that your networking elements all look like this, right, or bigger, essentially, right? They've assumed enterprise class 19-inch rack mount equipment. That isn't what you have in the home. What you have in the home is this kind of equipment, right? Little small consumer electronics devices that have no special support. They can't do any of these complicated protocols like SNMP that allow you to manage the network. What we have done is we've come up with a system for mapping the network that doesn't require any support from the system, from the network elements themselves, from the objects inside the network. And so we can map the network without any of that support. And that's what's novel. And it's also very interesting, actually, it turns out to be interesting even in the enterprise situation, because people do, Ian Kelly temporarily will, slap some small switch in somewhere and use it even in the enterprise environment. And the enterprise one would really like to be able to map the network and see those objects, and our software will be able to do that. So here's an example. Just a quick refresh of Ethernet. Ethernet's composed of segments, which in the old days was a long piece of coaxial cable, but in the new days is twisted pair and devices called hubs, and that creates a virtual coaxial cable, a single collision domain in which every packet goes everywhere. Also, Ethernet's composed out of switches, and switch has the property that it tries to improve the performance of the system by only directing packets along links where the packets actually have to go along that link in order to get to where it is that they're going. And a switch learns what it should be doing by observing the source address in a packet. If it doesn't know what to do with the packet, it sends it everywhere, but as soon as it's seen a packet from some machine X, it says, oh, I know that X is over there. If I see a packet in future that's going to X, I'll send it just over there, and I won't send it everywhere else. And switches and hubs have to be arranged in a tree in a valid Ethernet. And here's an example of the kind of topology that we can discover using our software. These blobs at the bottom represent the computers, and we've been able to use software running on these computers to detect some hubs and some switches in the network. We can't, however, solve, we're not perfect in all circumstances, and here's one of the ones where we're not. Or a couple of the ones where we're not. First of all, because a hub device is an object which is pretending to be this traditional piece of coaxial cable, it's impossible to tell the difference between one hub and n hubs that are directly connected, because each of them is just pretending to be a piece of wire. And so it just looks like one piece of wire. So we can't spot that particular configuration. Also, there's a certain arrangement of switches that we can never spot, which is this arrangement here. If you have a switch with exactly 2 links, and there are no computers on either of the links, then this switch effectively doesn't do anything. Every packet that comes in here goes out there, and every packet that comes in here goes out there. And so the switch does nothing, and so there are no side effects that we can observe, and so we can't detect that this piece of unnecessary equipment that's consuming electrons is actually in the network, so we'll not spot that. But we do most other things. Maybe. right at the end, on the kind of further work, when we have some ideas dealing with what do you do about computers in the system that aren't running our software. And we have a few tricks up our sleeve, but we're still to try them in anger. So maybe that will be a later talk one day. Right, how does this work? Well, in fact, what's happening here, we have a centralized distributed system. It's centralized in the sense that we have a single mapping of the system happening at any particular time. So in that sense, it's centralized. We're coordinating all of the information. But it's distributed in the sense that we're mapping the network by using all of the PCs, or as many of the PCs as we can, around the edge of the network. And so we're using a distributed system to collect information about how the network's behaving or to understand what's happening in the network. And we can, because of the way the system works, it's only possible to do one mapping at a time. So we also have to have a distributed mutual exclusion algorithm. When we coded this up originally, we did it as a peer-to-peer system. All of the computers in the network that we're using to map the network started out essentially having all of the information as the algorithm progressed. They knew what was happening in the system. But in fact, we discovered that's actually completely the wrong way. Peer-to-peer is completely inappropriate for this particular application. And so we redesigned it with as asymmetric a system as possible. We put as much intelligence as possible into the single centralized mapping agent, the master agent. And we make the slave agents that run on all the computers in the system as simple as we absolutely can, with as little intelligence as we absolutely can. And one of the reasons for doing this is because we want to get that onto as many different platforms as possible. The more accurate the topology map from the network, getting as accurate as possible a topology map out of the network is dependent on being able to probe the network from as many points as possible. And so we want to be able to put our software onto Windows CE, onto Xboxes, onto eHome devices, onto Microsoft's hardware products. Perhaps we can use the service packs to roll it out onto older versions of the system out there. It's quite a small component. And the smaller and simpler we can make that component, the more easily and more widespread it can be, and therefore the more accurate information we'll get about the topology of the network. So that's one reason for doing it. The way the master-slave protocol works, very simply and briefly, is the master sends a begin message and a broadcast message, and all of the slaves either sign in with respond with a hello message to say that they're available for mapping the network, or else they send a reset that says, no, actually somebody else is mapping the network at the moment, you should hold off. And that particular begin and hello response reset protocol is designed to include some probabilistic mechanisms to allow you to avoid an implosion of acknowledgements. If you have a very big network, say 1,000, you don't want a begin message to come out and 1,000 computers to respond and say, yes, we're here, because that would, you get an implosion at the guy who originally sent out the begin. So we have a probabilistic response mechanism based into that, where the probability is adjusted in successive begin messages, and the master can monitor how many responses are coming in and control basically the rate at which it adjusts the probability from 0 to 1. In various successive messages, so that it gets all of the responses in as fast as it can for the particular network it's attached to. If you've got a small network, they'll all come in quite fast. The probability will go up to 1 quite quickly. If you've got a very large network, the probability will rise up to 1 very slowly. And then once Damon. Yeah, this is Ethernet topology discovery. It's not working at the IP level, so it's completely below the IP stack. It's a separate Ethernet protocol, so it will work even when there's no IP on the system at all. Once a master has established a connection with the slave, then it can either cause the slave to send the topology probing packet into the network on its behalf, or the slave will record topology probing packets that it receives, and the master can ask the slave to send those back, report those back, and so it can deduce the network. And the slaves have the very simple state machine. The key thing is they have no idea why they're doing this sending or receiving of packets, topology probing packets. They're just doing what they're told. And this is another really good reason for making this not a peer-to-peer system, which is for intellectual property reasons. Because the slaves have no understanding of how the network is being mapped, we can give away, license, or make available reference implementations of this master-slave protocol and the slave implementation without giving away our control of, or our advantage, commercial advantage, which is how we actually map the network. So we could give away, publish how the master-slave protocol works, give away a free implementation of the slave, and still be in a position where we're completely in control of who can map the network, because only the master can map the network, and the slaves have no idea why they're doing anything that they're doing. Very simple picture of the implementation for those who understand the NDIS stack. Basically, we can either have the master and slave living up in the common language runtime and using this object called the NDIS UIO component. The thing on the left is stuff that already exists in Windows. This is the wireless zero configuration service. That's the thing that automatically signs your laptop into the wireless network if you have a wireless laptop. And it runs on top of this NDIS UIO object, which allows user space objects to talk to NDIS. So we can basically just copy that and allow a master and slave to talk to it. In fact, it's quite simple to take the code of NDIS UIO itself, which has some protocol code and some ERP code, which is a technical name to do with the Windows kernel, and copy that across and just keep the protocol code and put the slave code on top of that directly. And that makes it nice and small and simple. NDIS is all of the networking code in Windows. The network driver interface system? I don't know. Yes. Yeah, yes, yes, it's a plug-in driver for that, in the same way that NDIS UIO is. No. Security story. I just described this master-slave protocol in a way in which I said, well, the master can cause the slave to send packets on its behalf. And indeed, the master can cause the slave to receive packets and to send received packets back to the master. Now, hopefully, some of you might have started wondering what the security story was about the sending of packets on behalf of somebody else. Well, we do have a security story, and it goes as follows. First of all, most security boundaries are with respect to IP topology, or IP networks, rather than Ethernet networks. Specifically, if you already have a bad or rogue machine directly attached to your local Ethernet, then you're already in deep trouble. So, for example, such a machine might simply go into a tight loop sending broadcast packets, right, and attempt to consume the entire bandwidth of the network. Likewise, such a bad machine might deliberately create packets with lots of forged addresses and forged information in and send them on the local network and try and confuse ordinary communication. So, given that you've already got that amount of badness, what we were concerned about was, because this protocol is restricted to the local Ethernet and it can't be abused remotely, all that we have to do in terms of our security story is not make things any worse than they are already. And so our goals are to make sure that a bad or malicious machine on the network can't use the topology discovery service to put any more load on the network than it would do, for example, by if it was just constantly mapping the network, which is something that's completely reasonable for a system to do. For example, a network manager might deliberately set a machine up with a big display that just maps the network continuously and has a freshly up-to-date network, and that's quite normal behavior, so that has to be allowed. We've been quite careful to make sure that it can't be used for amplification attacks. That is, we can't have the bad machine causing many machines to attack an individual, rather than just the bad machine directly attacking another individual machine. We've also arranged it so that there's no address stealing possible. That is, a rogue machine may steal your address itself, but it cannot use this protocol to cause some other machine in the network to steal your address. And finally, we've tried to avoid any information leaking about the actual system that the software is running on, other than the very minimum, which either would be available again automatically to a rogue machine, or that would be available just by watching the network. So specifically, a non-goal is to be able to do mapping even in the presence of malicious machines on the local network. That's basically infeasible. A malicious machine on your local network can prevent communication on your local network, and that's not the problem we're trying to solve. A couple of techniques, very simple ones. I'm not going to go into the detailed techniques because this isn't the right setting. First of all, it's a technique which you might have heard of, even those of you who are not networking specialists, called Promiscuous mode. It's possible to put your network interface card into something called Promiscuous mode, in which it sees all of the packets on the local segment. Normally what happens is that your network interface card deliberately filters out addresses that are not for your machine to avoid bothering your machine, wasting CPU cycles, dealing with a packet that's not destined for you. It is possible to say to the NIC, please go into promiscuous mode, give me all of the packets that you can see. And so we can use this to work out some information about the network. First of all, we put cause all of the nodes to temporarily put their network interface card into this promiscuous mode. And then we provoke all of the nodes in the system to send the packet to the master. We can do this using this master-slave protocol that I described before. And then the nodes, because they're in promiscuous mode, are going to see, some of them are going to see some of these responses, depending on where they are in the network. And so all we have to do is collect back, again, using the master-slave protocol, collect back any possible response packets that were seen by any of the other nodes who weren't actually the source or the recipient of the packets that were sent in this step 2. And then it's pretty easy for the master to work out where the segments are in the network. A segment, again, as I mentioned before, a fundamental property in Ethernet is that all of the packets on a segment are seen by all the network interface cards. They're normally filtered out because a network interface card is not normally in promiscuous mode. But if it's temporarily in promiscuous mode, then machines on the same segment will see each other's responsive packets. And so when they're reported back to the master can observe that those machines saw those response packets. And so it can work out where the segments are in the network. Yes, you can get an asymmetry. If you have basically, as you have switches and hubs in your network and all of the packets in phase 1 here are going towards the master, what happens is that machines closer to the master may see a response packet from further away as it travels along towards the master. But you don't get the converse. So you can end up with an asymmetric piece of information when you do this. But it's fairly easy to knock the asymmetries out to give you the segments. And in fact, the presence of the asymmetries in that basically matrix that you get back is actually useful for a later stage for one of the more complicated algorithms that I'm not going to bother describing today. Right. So one of the properties of the begin hello mechanism at the start is that we arrange that all of the switches in the network know where everybody is. That's a normal state on a network, in fact, other than just shortly after you've turned the power on. But we actually explicitly make sure that all the switches know where everybody is in the network as part of the begin hello mechanism. So we know that packets are only being replicated here because of the behavior of hubs and not because of the behavior of switches, other than in the case where you might have a hub between a switch with machines attached to it. And that leads to asymmetry, which is a useful property for us. One other brief technique is what we call training. I described the fact that these switches learn information about where machines are by observing the source address. And that's actually one of the critical things that we use in all of our systems, all of our techniques, to deduce what's happening in the network is that we arrange packet transmissions through the network in such a way that just one or just some particular path of switches learn some piece of information. And then we probe the network to find out from where that piece of information is visible. So in this case, for example, suppose a machine creates some new addresses completely fresh, just pluck them out of thin air or get them from our software, A prime and A double prime for machine A. Then it can arrange here that some switch, if it sends a broadcast packet, its notation here means machine A sends a packet, its source address A prime to the broadcast address. And all switches know where A prime is. And so if A then sends a packet from A double prime to A prime, only the switch directly connected to A will learn about A double prime, because this packet won't get forwarded. The switch will think that A prime is on the same link as A, the same segment as A, and so it won't forward this packet, but it will observe it, and so it will learn about A double prime, and none of the other switches in the network will have learned about A double prime. Yes. That's standard practice on Ethernet, that you just put in whatever you like. I mean, normally you put in your own address, that's convention, but there's nothing to stop you lying. That's why if you have a bad guy in your local network, it's pretty bad. So here's an example of where this is useful. Briefly distinguish the left and right-hand case. If both A and B in turn, first A and then B, send a packet from the same address, made-up address, they both claim to be that address, and they send it to their local switch in the technique that I've just described, then in the left-hand case, the two switches each believe that this address X is attached to the link attached to them, and in the right-hand case, the second packet will have updated the switch. So when we send this packet here, A goes in the third stage, A goes back and sends a packet to this magic address X. And we can ask the question, does B receive this packet? And the answer is only in the right-hand case. Because in the right-hand case, the second packet has updated the table in the left of the switch that A is directly connected to. And in the left-hand case, the second packet has not, because it wasn't seen by that switch. So here's an example where we can use this basic technique to infer, understand some information about the way the network is connected. So to summarize, future work, we still have some work to do on techniques for very large, complicated networks. We're in the process of writing up a patent from various of our techniques. We haven't yet addressed wireless in full. We have some ideas there, but we've yet to test them out in anger. And as Simon asked earlier, we would like to be able to try and use some information that we can from legacy or other nodes in the system that aren't running our software to help us understand about the network. And finally, of course, is to make this plug this information into the kind of work that Dean and Peter are doing and various others in terms of quality of service and understanding bandwidth availability, make use of the understanding the topology of the network to do that better. And finally, of course, transfer to product and ship it and make all of our customers happy. So the one-slide summary is, this is a software-only way of doing topology discovery of Ethernet. It needs no support from networking equipment, but it works with your standard cheap consumer equipment. And it's got a whole bunch of uses, including network diagnostics, doing quality of service, video stream admission, making even performance recommendations and that kind of thing. And there's a SharePoint site with lots more information on, or you can see either me or Austin for all of the gory details.